Hi, my name is Alessio, and I'm glad to present you today the CORSMAL challenge on audiovisual object classification for human-robot collaboration. Before starting, I would like also to thank the other organizers, Ik, Timothy, Ahalya, Berk, and Andrea. The CORSMAL challenge is about understanding from audiovisual data different physical properties of household containers for food and drinks. These containers are manipulated by a person prior to a human-robot collaboration and could be relevant for assistive scenarios at home or in a workplace. As you can see from the examples, containers can vary in their shape, size, weight, or appearance, or they can be occluded by the human hand during manipulation. Our challenge provides a benchmarking framework that supports the design and evaluation of novel audiovisual solutions for the estimation of the physical properties of containers in these challenging scenarios. The solutions should be accurate, robust, safe, and adaptive to changing conditions in the context of human-to-robot handovers. Given an audiovisual input, we define 5 tasks for the challenge. Each task is associated with a physical property that should be estimated by the algorithms. The goal of the first task is to classify the amount of content within a manipulated container as empty, half full, or full. The goal of the second task is to classify the type of content, if any, within a manipulated container as water, rice, or pasta. The goal of the third task is to estimate the capacity of the container. The goal of the fourth task is to estimate the mass of the container. The goal of the last task is to estimate the width at the top, the width at the bottom, and the height of the container. CORSMAL containers manipulation is the reference dataset for the challenge and contains 1,140 audiovisual recordings of 12 people manipulating 15 different containers with 3 different types of content. The dataset was acquired with a multimodal, multi-sensor setup consisting of 4 RGBD cameras and a circular array of 8 microphones placed under the fixed robot view. Each recording corresponds to a configuration that consists of a person manipulating one of the 15 containers with one content at a predefined amount. The configuration was also acquired in a specified scenario, background, and illumination condition. For the challenge, we split the dataset based on a selection of the containers into a training set, public test set, and private test set. We also identified 3 manipulation scenarios that have increasing difficulty levels due to hand occlusions, person entering the field of view, and different dynamics and actions performed by the person. In the first scenario, the subject sits in front of the robot while a container is on a table. The subject either pours the content into an empty drinking glass or cup while avoiding touching the container, or shakes an already filled food box. Afterwards, the subject initiates the handover of the container to the robot. In the second scenario, the subject sits in front of the robot while holding a container before starting the manipulation. The subject then initiates the handover of the container to the robot. In the first scenario, a container is held by the subject while standing to the side of the robot, potentially visible only on the third-person camera view. The subject manipulates the container either before or while walking in. When in front of the robot, the subject initiates the handover of the container. As the goal of the challenge is also to target human-robot collaboration, we provided a real-to-simulation framework that validates the physical properties estimated by the participants to the challenge into a simulated human-to-robot handover scenario. To achieve this, the first three tasks are combined to estimate the filling mass with a non-linear formula. The filling mass is then added to the container mass to provide the estimated object weight to the simulator, along with the estimated object dimensions. For fairness across the challenge solutions, the simulator takes additional object annotation as input to make the task as reproducible as possible, and therefore only the predicted physical properties should impact the performance. The simulation then visualizes and assesses the object safety and the delivery accuracy. We define object safety as the probability that the force applied by the robot enables a gripper to hold the container without dropping it or breaking it. For the delivery accuracy, the container should be placed upright and within the predefined target area. Here are two examples of our simulated human-to-robot handover using physical properties estimated from real video recordings of the public test set. As object annotations, we included an offline reconstruction of the 3D container shape, the true object weight, and the object pose over time. The container shape is rendered in the simulator using the true object weight. However, the weight does not affect the robot control, but it is only used for validation of the object safety. The object pose is manually annotated every 10 frames, and we then perform interpolation in the intermediate frames. This can result in non-realistic motions compared to the real video, for example, in the shaking movement of the video on the top. In addition to the tasks, the dataset, and the simulator, we computed 13 performance scores to provide sufficient granularity into the behavior of the various components of the audiovisual algorithms and pipelines. The first 7 scores directly quantify the accuracy of the estimation for the main challenge tasks. Other 3 scores evaluate groups of tasks and assess filling mass estimation, joint filling type and level classification, and joint container capacity and dimensions estimation. Other 2 scores are an indirect evaluation of the impact of the estimation on the quality of human-to-robot handover in simulation. I would like you to pay attention that the scores for filling mass, object mass, and post-delivery may use random estimations for either of the tasks not addressed by an algorithm. For filling level and type classification, we computed the weight average F1 score. For the other measures, we computed the relative absolute error followed by either normalization function or exponential function to convert the error into a score. We also included an indicator function to account for configuration not estimated in the test set by an algorithm. The overall score is then computed as the weighted average of the first 10 scores in the table. The challenge received submissions from 3 teams. 3 algorithms were submitted for the container mass estimation. 2 algorithms were submitted for estimating the capacity and dimensions of a container. 2 algorithms were submitted for classifying the level and type of the content. Algorithms use different modalities for solving the different tasks. For example, there is a preference for the audio modality when classifying filling type and level, but one team used both audio and vision. Vision is instead preferred for estimating the container properties for estimating the container properties. 2 teams used the visual data from the front fixed view, while one team exploited all the 3 fixed views. Most of the algorithms used efficient or shallow convolutional neural networks. On the contrary, one team exploited the recent transformer model for classifying filling type and level and used a multi-view geometric approach for container capacity and dimensions estimation. All teams also use object detector or instance segmentation to identify the container in the videos for estimating the capacity, mass, and dimensions of a container. The algorithms of the teams have been ranked across 10 leaderboards that cover the individual tasks, the group of tasks, and the overall score for the public test set, the private test set, and their combination. The leaderboards on the website also contain past challenge entries and baselines. Here are some of the leaderboards, and you can find all the results on our challenge webpage. In this table, we focus on the results computed on the combined test sets of the CORSMAL container manipulation dataset. And we compare the algorithm submitted by the teams and two baselines. One baseline estimates the properties with a pseudo-random generator, and the other by using the average of the training set for container capacity, mass, and dimensions. The algorithms designed by Wang's team are the best performing across most of the scores, including the overall score of the challenge. The algorithms of Matsubara's team achieved the best performance for container capacity, filling mass, and the joint estimation of container capacity and dimensions. The algorithm of Apicella's team achieved the second best performing score for container mass. To recap, the CORSMAL challenge is a benchmarking framework that supports the design and assessment of audiovisual algorithms for the estimation of the physical properties of containers manipulated by a person. For the challenge hosted at ICASSP, we defined 5 tasks and 13 performance scores, and we facilitated the comparison by ranking the algorithms across 10 leaderboards. We also introduced a real-to-simulation framework for visualizing the safeness and assessing the accuracy of the estimation within a simulated human-to-robot handover scenario. The framework allows participants to understand the impact of their solutions even when they do not have the robot available or when a person is manipulating a fragile container. The challenge is not over. If you are interested, you are welcome to check out our challenge webpage. We are looking forward to receiving your submission.